Hey everyone, it's Carver here, and in this video we will be covering logistic regression. We will be having a brief overview of the theory of this algorithm, and then we will straight away jump into its implementation. I won't be going into much details of how this algorithm really works behind the scenes and the maths involved, or the equations that you see here. Where do these equations come from? I won't be covering that. For that, what I can recommend you guys is to check some other tutorial that is covering the theory for this algorithm, and there are lots of such tutorials on YouTube. In fact, this is the very reason I'm making this tutorial, because when I was implementing this algorithm from scratch, I couldn't find any good source which covered implementation part of this algorithm. So I had to pretty much do everything from the ground up myself without any help. But anyways, now that I have done, I thought I can make a video out of it and put it on YouTube so that it might just help someone someday. So anyways, starting with the tutorial now. Logistic regression basically is a classification algorithm, and what that means is if you just pass it something, it can classify it for you that whether the given thing is um, this or that, basically. So if you have an email classifier, what it can do for you is that it can classify for you whether a given email is is a spam email or it's a non-spam email. So that's pretty much that what classification is in a nutshell, and that's exactly what we'll be doing in this tutorial, except we won't be working on the emails. Rather, we will be working on this dataset called MNIST dataset. So this dataset basically is images of handwritten digits. Each image is 20 by 20 in size, and there are 5,000 such images. If I just go over to the dataset, so this is how the actually dataset looks like. We have 5,000 images over here. Each row represents one image, and then we have 401 columns over here. Each column represents one pixel value in any given image. So why 400? Basically the image size is 20 by 20, so if you multiply 20 by 20 we get 400 pixels. So yeah, that's where this 400 thing comes from. But in the last we have another 401 column, which basically is a labels column, and what it means is that this column is basically telling us what this picture is of, what is this picture is of. So if I just select some row and it says 3, what it means is that all this data in this row, if we were to transform it into all this data, if we were to transform it into a shape of an image, then it will be an image of digit 3. Similarly, we have 4s, 5s, 0s, 1. We have images from 0 to 9. We have almost like 500 images for each digit. Yeah, almost 500. So this last column is our labels column, and the rest of these 400 columns are our input columns, or the input data. So this is the data set we are dealing with. Go over to the data set. So this is how the actually data set looks like. We have 5,000 images over here. Each row represents one image, and then we have 401 columns over here. Each column represents one pixel value in any given image. So why 400? Basically the image size is 20 by 20, so if you multiply 20 by 20 we get 400 pixels. So that's where this 400 thing comes from. But in the last we have another 401 column, which basically is a labels column, and what it means is that this column is basically telling us what this picture what is this picture is of. So if I just select some row and it says 3, what it means is that all this data in this row, if we were to transform it into all this data, if we were to transform it into a shape of an image, then it will be an image of digit 3. Similarly, we have 4s, 5s, 0s, 1. We have images from 0 to 9. We have almost like 500 images for each digit. Yeah, almost 500. So this last column is our labels column, and the rest of these 400 columns are our input columns, or the input data. So this is the data set we are dealing with. Okay, so in the first step, what we will do in logistic regression is that we will try to fit a linear line onto our input data. So our input data is basically the first 400 columns except the last column. The last column will be our output data represented by Y, and all these columns on the left, the first 400, are our input data represented by capital X. So we will be trying to fit this linear line onto our data. We have these two parameters over here, weights and bias, which we'll be learning throughout the training process. But initially, we will initialize the weights and bias with some random values. Weights especially has to be of this shape, 1 cross 400, which basically means we should be having one weight for each column or each pixel. So in the next step, we will be passing this linear equation into this function called sigmoid function, and the reason for that is this linear equation over here gives us continuous data, not in the form of zeros and ones. And why is that important is that basically in logistic regression we are interested in classifying a thing between in a yes or no fashion. What I mean is that we just want to know that if something is present or it's not present. But the problem with linear equation is that it doesn't do that. It just gives us some continuous random values. Not exactly random, but continuous values. So they are not exactly useful in our scenario. So what do we actually do? Luckily, we have this function called sigmoid function. What it does is it will transform your input between the range of 0 and 1. So if you give it any input, it will transform that input in between the range of 0 and 1. But still, it is not doing what we really want from it. It is giving us values between 0 and 1. What we really want from it is that it gives us values 0 and 1. So what we can do here is we can use threshold. So how it works is, if our output value from this hypothesis is this sigmoid function is greater than the threshold value, which is let's say we have set it at 0.5, then we will take the output as 1, and if it is below the threshold we will take it as 0. So let's say our sigmoid function is outputting a value of 0.62, which is greater than the threshold value, then we will take it as this 1, and if it was below the 0.5, then we will take it as 0. So this sigmoid function together with threshold will give us values between either 0 and 1, not between. So this is pretty much what is happening over here. We have these inputs. We're passing these inputs onto the linear model. It will be giving us some continuous values, not exactly probabilities, but just the continuous values. Then we'll pass these continuous values onto the sigmoid function, which will give us values between 0 and 1. And then finally we will apply a threshold function over here, which will return us values either 0 or 1. So now that we have our outputs in the form of zeros and ones, what we want to do is we will like to calculate how good or bad our predictions actually were. So for that we have this cost function over here. What it does is basically it will try to figure out our outputs, our predictions with the actual outputs in this last column, and it will try to output some value for us. And the greater that output number from this function is, it means the worse our predictions are. So our goal is to minimize the values from this cost function over the period of training. And to do that, we have this thing called gradient descent over here. So how this gradient descent really works is that if we try to plot the above function, it gives us a shape of something like this. The cost is decreasing from as we move towards the bottom. So all we want to do is to be at the bottom where the cost is minimum. In the starting, we will be somewhere at here or here at some high place, and the goal will be to travel down the hill towards the valley, towards the bottom of the valley. For that, we will be taking slopes at different points, and by using slope, we will be knowing where the downhill is, and we will be just traveling in the direction of the downhill. And when we will be traveling, we will be taking different steps, and how big or small those steps will be, that's actually determined by this hyperparameter called alpha. This is called a hyperparameter because we declared the value of this hyperparameter before the training itself. So it is something that we just declare before the whole training starts. If the alpha parameter is too small, which means is if you are taking too small steps, it will take a long time for our algorithm to learn and reach the bottom. And if the steps are too large, it will just start jumping over the valley and skipping this bottom over here. So we have to choose some optimal value for this alpha. So in these steps so far, we have covered pretty much what a training really is. But the problem is that after this whole training process, we will be having a classifier which is able to classify just for one digit. What it means that it will just be able to classify whether a digit is 0 or is it not 0. So that's it. But what we want from logistic regression is that it can classify for us for any given image what digit that really is. So for that, we use this technique called one versus all. And what we'll do in here is that we train 10 different classifiers, one for each digit, and then we will simply give an input image to all these classifiers, and we'll take the probabilities of each classifier, which is the hypothesis value. It will be returning values between 0 and 1, each classifier, the 10 classifiers for any given image, which is actually a measure of how confident a classifier is about predicting some image that is given. So we will just simply listen to the most confident classifier. Let's say different classifiers give us different inputs from 0 0.3, 0 0.2, 0 0.5, 0 0.7, 0 0.9. So the 0.91 is pretty confident that this given image is whatever I'm trying to classify. So we will just simply listen to him, and we will try to figure out what that classifier is predicting, what that digit it is trained on. So we'll simply take the digit, and this is basically one versus all classification. So the steps to implement this logistic regression in code are pretty straightforward. The first step we have to do is we have to create 10 binary data sets. So what a binary data set is, basically we have to make a new data set for each classifier. So a data set basically is like, let's say we are making a data set for digit 2. So for 5,000 images, we will just be telling what images in those 5,000 images are of digit 2 and what are not of 2. And how we will do that exactly is by going to the last column, and wherever there is not 2, we will just place the value of 0 there, and wherever there is 2, we will place the value 1 there. So what this will mean for our algorithm is that it will be telling our algorithm if there is somewhere 0 in here, we are saying that this whole image is not an image of 2. But if there is 1 here, what our algorithm will learn from this is that this image is of digit 2. So we will make 10 binary datasets, one for each classifier. Then each dataset we have just created, in the second step we will try to split it into input and output data, the input data being the first 400 columns and output being the last column. Then we will train all the classifiers on each dataset individually, one by one, and in the last step we will be grouping all these classifiers together to give us this one versus all classifier. Then we will be checking accuracy for an individual classifier, and we will be plotting the cost functions. And lastly, we will be checking the accuracy of one versus all classifier on the original data set. That is, we will be passing any value, any image to the classifier, and we will try to see what that image is of. Like, is it of 2, 4, 5, 9, or whatever it is. So let's just move towards the code now. So here's the code, and for a quick walkthrough, first we will be dealing with the data part here. We will be creating multiple data sets. Then we will be training classifiers, and then we'll be predicting accuracy for each classifier. Actually, not predicting accuracy, we will be calculating accuracy for each classifier. And then we will be plotting these cost functions for each of the classifier to visualize our training. And then finally, we will be checking the accuracy for our one resolve classifier. Okay, now towards the goal. Firstly, we will import the necessary imports that we have to make, the necessary libraries that we'll be using. So firstly, I'm importing NumPy for numerical calculations, pandas for file operations, and matplot for plotting purposes. Then I'm going to download the dataset from my Google Drive. And then in the next step, we will be reading dataset into this variable data using the read CSV function. I'm setting the header equals to none so that it doesn't treat the first row as the header. Then I'm making 10 deep copies of this data into 10 different variables, which will be the 10 binary datasets. Then I'm putting these 10 datasets into a list so that's more organized. Then in here, I am making the 10 binary datasets. This is a very easy step. I don't think I have to really give any explanation here. What I'm just doing is that for each image in the whole dataset, which are 5,000 images, I'm just accessing the last column, and for each binary dataset, for each digit, if that digit is present, we are putting there a value of 1, and if it's not, we are placing there a value of 0. So we are creating the binary data sets over here. Then in the next step, we are doing this step here, splitting the input and output data, and we are storing that in a dictionary. And what a dictionary really is, it is basically a dictionary. Just like in real world, we have dictionary, we have some words in it and meanings and definitions assigned to it. So for any given word in a dictionary, we have some definition or meaning assigned to it. So just like that, in here, we can have some key, some unique key, and then we can assign some value to it. It can be integer or list or whatever you just want to store. So I'm creating this train test data dict, very strange variable name. But anyways, I'm creating this dictionary over here. Then in this dictionary, I am, for each key by the name of like D0, D0, D1, D2 up till D9, I am storing inputs and outputs datasets X and Y. So for example, I have three key values like D0, D1, and D2. For each so for each key, I'll be having this value pair of X and Y, which is basically a list containing X and Y. So D0 will return a list of X and Y, and on the 0th index of D0, it will return me the input data, and the 1 index will return me Y data. Now that we have performed all the necessary operations we have to perform on the dataset, the next step we have to perform is to train the classifiers. So this is the main code where all the training is happening. Firstly, here I'm initializing this variable called iterations here, and I'm just giving it a very big random value. And the reason for that is I don't want my training loop to just stop because I'm giving some small value over here. So I'm giving a very large value so that my loop keeps looping, and it doesn't break before the training actually stops itself. Actually, I could have used while loop, but I'm just more comfortable with for loop, so that's why I just went with this. uh, Anyways, then I'm initializing the alpha value here and m value. The m is from this cost function over here, which is basically your length of your dataset. And alpha over here, actually I tried different values for alpha, and 0.160 turns out to be giving me really good accuracies. So that's why you see 0.160 over there. Generally, the alpha values are small and between like 0.1s and 0.01s, something in that range. So you basically have to experiment with these different values to see what value is giving you the best accuracy. And then I'm creating two lists over here, one for storing the cost values for all the classifiers so that we can later on see how the training of individual classifier went. And then I'm creating this this list for saving the trained parameters, which will basically be the weights and biases for each of the classifier. We will get into it when we reach there. Anyway, so in the loop, we are firstly accessing the x and y's for each given dataset from the data dictionary in the last step. So when the loop is at 0, what we are getting is we are accessing the D0 key, which will return us an array of x and y. So when I put 0 here, I'm saying is bring me the value at index 0 of this list, which is x. So it will return me x, and I'm storing it into x. And so similarly, if I put 1 here, it will return me the value at the 1 index, which will be the y, the output dataset. Then I'm randomly initializing weights with random values. The shape is of 1 row and 4 column. I'm initializing bias with 0. You can initialize it with basically any value. It doesn't really matter because it's going to change in the training loop anyways. Then I am initializing another list for storing cost function values for each classifier that we are training on at the current moment. So this list will actually be holding cost function values for one classifier, like for classifier 0. What we will do is we will dump these values into this list. So this cost values will be actually become a list of lists. So at each index of this cost function values, we will have a list of cost function values for dataset 0, 1, 2 up till 9. Okay, so moving next, I'm just declaring this random variable k for keeping count of total number of iterations that it takes to train one dataset on for one classifier. Then moving towards the training itself, this is the training loop. Firstly, we will fit the linear equation, and then we will pass the values we get from this linear model into the sigmoid function, which will output us values between 0 and 1, which will actually be the probability for a number to be existing or not. Firstly fitting the line, then calculating hypothesis and calculating the cost function for dataset 0 for classifier 0, and then storing the value it gets from this cost function into this list for cost function 0. And once the training is over, we will be dumping this cost function value we are appending over here into the cost values for total datasets in here. Okay, moving next, we have this gradient descent over here, which is pretty straightforward. I just coded the equations over here. There's nothing really to explain over here, so I'll just skip that. Okay, so now we have to figure out how we have to actually stop training, and for that we have to put in place these conditions you see here. And what this exactly is that we are just taking this cost value this function is returning over here, and we will be taking the difference between we're taking the difference of this cost value with the previous two cost values calculated in the previous two iterations, and if that difference is very negligible, then we will just stop the training. And the reason for that is, if you try to visualize it, it means is that we are already at the bottom over here, and at each iteration we are not moving any further, so we are already at the bottom. So if the difference between the consecutive values is very small, so it means we have already reached the bottom. We have to stop the training. So this is exactly what I'm doing here. I'm checking the second last and the third last value. Actually the second here is just because I'm appending the values here. So if I write -1 here, I'm just basically accessing the very value I'm calculating in this iteration. so which is not what we are interested in. We want the last value from the current iteration, so that's why we have -2 over here and -3. Then finally, once this loop breaks, we append these cost values into the we append these cost values for one classifier on a given data set into the cost values list defined above here, which will be containing all the cost values for all the classifiers. And then also we are storing the weights and biases, because training after all is all about getting to know the best optimal values of weights and bias. So we have to save these weights and bias somewhere so that we can use them later. So I'm just putting these values into a list of trained parameters. So trained parameters will become list of lists containing weights and bias for each data set, starting from index 0 for data set 0 and up till data set 9 at index 9. So the output from this function looks something like this. Like here it's telling is that it is training for data set 0, and the starting cost for the function, so the starting cost when the training started was this, and then when we ended the cost was only this. It took only 14,000 iterations to train on one dataset. So now that our all classifiers are trained, our next step is to check accuracy for individual classifier. So if I just minimize this cell over here. Okay, so in this cell we will be predicting the accuracy for each classifier. Oh, okay, not actually predicting. We will be calculating the accuracy for each classifier. So what's happening over here is I have created a loop. In this loop I'll be iterating over the dictionary, and for each iteration I'll be getting input data for dataset 0 in the first iteration, the output dataset y for the 0 dataset, for the dataset of digit 0. Then also I'll be fetching value for the trained weights and bias from trained parameters list v. Then what's happening over here is that okay, sorry, I forgot this one. This variable will just be for keeping track of number of accurate predictions we are making. Okay, then in this loop what we are doing is we are visiting each picture one by one. So that's why we have 5,000 iterations. So firstly we are trying to fit the linear line onto one image. So we have to first access one image this time. So we don't have to pass in the whole dataset. We have to pass in just one image at a time. So that's why this iLock is here. So what it's saying is that give me just this row and all its columns. So just give me one image. And what image exactly? This image I, which is going to be changing from 0 to 5,000. So once we have fit this linear line over here, we'll pass this value into the hypothesis function, the sigmoid function. Then, okay, let me just write it here. Okay, then this sigmoid function will give us an output of the probability, or in simpler words, how confident my classifier is in predicting that particular image. Okay, so once we have this probability from this function here, then what we need to do is that we have to check whether what our function hypothesis is calculating, is it actually the case that that digit is indeed present in that place. So for that, what we have to do is we will just simply check the output column in that particular place. So firstly we will take the value from our hypothesis. This is the threshold we are applying here. So if the value for hypothesis is greater than 0.5, we will take it as 1. And so if we have taken it as 1, if it is greater than 0.5, and we are confident that our classifier is saying that yeah, that specific digit is present at this place, so we have to just double check with the output column that is it indeed true that that digit is present over there. And if it is the case that that digit is present in the output column, we will just simply increment the correct prediction variable. And what we also have to do is, when our hypothesis is saying that it's not confident about some value, that this value is present over there, in simpler words, it's basically saying that I'm sure that this digit is not present here. So we have to check for that too. When our hypothesis is saying that I'm not confident that this value is present over there, so we have to just again double check, is it indeed true that that digit is not present over there in the output column. So again, if it's the case, we will just increment the number of correct predictions, and in the end we will divide the number of correct predictions that we made divided by total number of predictions that could be made, or the total images that we have, which is 5,000. So multiply that with 100, and that would give us the accuracy. And so this loop will keep running 10 times for each dataset, and this will give us the accuracy for each dataset. So these are the accuracies we got from this code over here. And if we are to plot these functions, which will basically be plotting the cost values, which we defined over here, this one. So this again is containing a list containing lists at each index. So at index 0 we have list of cost values for classifier 0 on dataset of digit 0, and on 1 for 1, for 2 for 2. So just like that. So if we plot these values over here, we can see how from the starting point of the training, the cost function was the value for the cost function was so high that we were making, in simpler words, we were making very wrong predictions. And then slowly, as we trained the model, we decreased the number of the scale of wrong predictions we were making. So it turns out to be less and less bad as we started training the whole thing. And when the training ended, predictions we were making compared to the actual output were not really bad at all. We were hitting a really good accuracy over here. If you just see, they are really flat, almost touching this bottom line here. Okay, so now we are moving towards our last step, which is calculating the accuracy for one per all classifier. This step is very much similar to this one. What we have to do is we have to basically pass each image to all the 10 classifiers, and for each classifier we have to take their predictions, their probabilities for a given image that the sigmoid function will output, and from those probabilities we will just pick the probability which is the highest, and we'll just listen to that classifier. So what's happening over here is that I'm accessing the inputs and outputs input output column of the original dataset, not the binary dataset this time, because we have to make the one versus all classification on the original dataset. Then if you see here, we have a 5,000 loop and then a 10 iterations inner loop, and this is exactly the opposite of this one. So the reason is that we have to access all the images one by one. So we have to pass images one by one to all the 10 classifiers over here. So firstly we will pass one image to classifier for 0, then 1, 2 till 9. We will calculate the hypothesis for that, which is basically the confidence value of each classifier, that how confident that classifier is in predicting a given image. So we will be appending those confidences or those predictions into a list. Then once we are done with these 10 classifiers for one image, we will be choosing the maximum of those probabilities, the highest of those probabilities. Let's say the 10 classifiers are predicting values like 0.2, 0.1, 0.3, 0.5, 0.7, and 0.9. So 0.9 being the highest, but we will just simply listen to that classifier who is most confident in predicting something. So we are firstly going to take the maximum of the probabilities, then we are going to take the index which that maximum sitting at. So we'll have so it will actually give us the classifier. In this way we can identify the classifier which is predicting the image with the most confidence. So then all we have to do is check whether the prediction that the most confident classifier is making, is it actually the image present in the output column at that given location. So if it is, then just make an increment in the number of accurate predicts. Then at the end of this loop, we get the number of accurate predicts, which is 4693, and dividing this by 5000 will give us the accuracy, and which is almost 94%. So this is all for the logistic regression, and I'll just link my GitHub repo in the description below, where you can find this collab notebook if you want to try the code for yourself. And if you have any questions or you see any problems with the code, you can just comment down in the comment section. So have a great day. See ya.